Hello there. We take a look at the solutions to problem set number 11, where we talk about homomorphisms. So, phi is a homomorphism from G to H, and I do not use different symbols for the operations in G and H now anymore. In the video from lesson 11 we used G in a circle and H in a heart, a little heart, so here I only use a dot for both groups. So first of all we have to show that every homomorphism maps the neutral element of G to the neutral element of H. Okay, all we know is that a homomorphism respects the group operation, so somehow we need to have as an argument here the composition of two elements. So we simply write the neutral element as E times itself, and this times here is the group operation in G. Now phi is a homomorphism, so maybe like that. This here is the composition in G, and this here is the composition in H. And now if I look at these two expressions here, they're the same group element in H, and by the cancellation law I can cancel or if you do not remember the cancellation law, simply use that you are in a group, so this element has an inverse, so you can multiply from right or left with this inverse, and then you end up with EH here, and on the other side with the image of EG under phi, and that's it. So it's good to remember homomorphism always maps identities to identities. Okay, next we have to show that if I map the inverse of an element, I could as well map the element first and then take its inverse in H. We're talking about the inverse of this element, so I write down this element of H and multiply with this here, because the claim is that this is indeed the inverse of this element. Now phi is a homomorphism, so this here is the same as that. That's the fundamental property of a homomorphism. Again, this here is composition in H, this here is composition in G. Now this here gives me the neutral element of G, but we just showed that this here is the neutral element of H. So this indeed means that this here is a right inverse to this, and as we've shown long before, this automatically means that it's also a left inverse. Or you could also write down this here in the other direction. Maybe this is the best way. We know that this here as an element of the group H has an inverse, so we multiply with its inverse from the right. Then here by associativity it cancels, and we are left with this here, and on this side I am left with this here, and this is what we wanted to show. Now if you're getting used to working on this abstract level with the axioms and the properties of a homomorphism and the group in general, this is a very easy exercise, but as a beginner I remember that I even struggled with stuff like that, because here you need to have some idea. At the beginning level I looked at that and thought, well, okay, yeah, but how do I get the -1 outside there? So do not feel bad if you're still struggling a bit with stuff like this. Okay, next exercise. We are supposed to show that this map here, squaring a group element, so multiplying it by itself, is a homomorphism if and only if the group is abelian or commutative. Before writing it down perfectly, let's first collect some ideas. So being a homomorphism means that for all group elements G and H, this here is true. Now here there's no need to distinguish these dots because we are in G. Phi is a map from G to itself. So to be a homomorphism we need that, and this here is G squared times H squared. So maybe it's best to do both implications separately. Okay, so this does not really belong here. So we assume first that G is abelian and we take two arbitrary elements GH of G. Then we have phi of G times H is by definition GH squared, but this is GH composed with GH. But now, since G is abelian, I can switch the orders here and I end up with G squared times H squared, which is exactly what I want. So phi is a homomorphism. Write that down for yourself. Okay, now for the other direction, assume that phi is a homomorphism. Then, by this property here, this here simply means GH squared is the same as G squared H squared for all group elements. By this here, if you write down the proof, you could put that there. And then on problem set 4, exercise 3, we already showed that this is actually equivalent to being abelian. So you could sum up the whole proof by simply writing down this here and then citing this exercise, but I think here it is no mistake to split it up into two parts, because here this is about getting used to the concept of a homomorphism. Okay, but the key to the whole exercise here is really what we proved back then. Okay, in the next exercise we take a look at an example from analysis. We take the well-known exponential function. This doesn't seem to fit with our algebraic approach here at all, but remember that there is this well-known power law for the exponential function, namely that e to the x plus y is the same as e to the x times e to the y. And this is exactly the homomorphism property if you take here the real numbers with addition as group operation. This clearly is a group. And as the image group, you take the positive real numbers together with multiplication, which also clearly is a group. And then you see, you have exactly what you want a homomorphism to satisfy. Here, exp applied to the sum, so the group operation here, is the same as exp applied to those guys first, and then combining in this group here with multiplication. So the exponential function also is an example for a homomorphism of these groups. Okay, now exercise 4 is maybe a bit hard to understand at first. Let me give you a hint and then you can fill in the details by yourself. So we take the square, but we do not label the vertices 1, 2, 3, 4 and so on, but we simply take a look at the diagonals, so we forget information. So same as in example 2, where we projected from the integers to z mod 2z and only even or odd was important. Let's take a look at what the reflection about this axis here does with the diagonals. If I reflect the square, so this green diagonal becomes this green diagonal, which is what diagonal 1 was to begin with, and also here, the red one goes to the place of the second green diagonal. So in permutation notation, I would say that 1 here goes to where number 2 was, and diagonal number 2 goes to where 1 was. So this is the transposition 1, 2, which I call tau. And now my homomorphism maps here this symmetry to this transposition, which is clearly an element of S2. So now the identity, of course, changes nothing, so it becomes the identity here, which would be in cycle notation 1 and 2, nothing gets changed. What does the rotation do? If I rotate by 90 degrees, then I end up with tau, because now they get swapped around as with the reflection S. If I rotate by 180 degrees, nothing happens. So I end up with the identity. And if I rotate by 270 degrees, there, then again the diagonals get mixed up, get swapped. Now here we already saw that this here is tau, and this here should be the identity. Why? Because if I swap the places and rotate by 90 degrees, nothing changes for the diagonals. So this is the identity, and so on. Do the last two cases by yourself. So this clearly is a map from D4 to S2, but is it also a homomorphism? Why, yes, mainly for geometrical reasons. So if we take R composed with S, for example, this should be the same as this here. Is that true? Well, here we found out that this is the identity. This here, phi of R, is tau. Phi of S also is tau, but tau is a transposition, so tau squared again is the identity, and so on. So you can think this through or simply say, well, for geometrical reasons this is somehow clear that this holds. Especially if you're a good geometrical thinker, then you can visualize all these here in your mind and see that this is true. Now, what is really behind this is, what do we do to find out what both sides are? Well, here we apply R and S to the whole square and then look at the diagonals. And here we look first at the diagonals, what happens to them in each step, and then combine these steps. But it is clear that both yield the same result, right? If you first apply the whole symmetry and then look at the diagonals, or if you first look at the diagonals and then at the combined effect, it's clearly the same. But I'm not going to formalize that here anymore, so that's just a nice geometric example for constructing a homomorphism. Okay, next exercise where you need a little bit of knowledge about matrices. So first of all, why is this a subgroup of GL2F? Well, first of all these matrices clearly lie in GL2F because their determinant is 1, so they are invertible. And if we take AA and AB inverse, well, this argument is not required in the exercise, but I think it's good to do it anyway. The inverse matrix of the matrix 1B, 0, 1 is simply that you change the ones, that if with the help you interchange these ones here, that has no effect, and you put a minus sign here. Sorry, it's supposed to be that. And this here by matrix multiplication 1, 0, 0 minus B plus A. So this is A minus B and this is 1. So this again is an element of H. H is clearly not empty, so we have a subgroup. Now the map phi from the field F to H simply sends an element of the field to this corresponding matrix, which we call A sub small a, and we take a look at phi of A plus B, because here our group operation is addition. This is the matrix 1, 0, A plus B, 1, which is the matrix of A plus B. Then we take a look at the images of A and B taken first and then combined here in this group, so this here means matrix multiplication. And we almost did this above. So by matrix multiplication, this here is this matrix, and those are clearly the same, and this does not depend on the choice of A and B. And this simply means that this phi here is actually a group homomorphism. I can't stress this enough. If you write down these as solutions to an exercise sheet or problem set that you hand in, please use more text. Do not simply put down those calculations here, but say, all right, I take two arbitrary elements A, B of the field, and then I calculate this here, and next I calculate, and so on. That's always better and better mathematical style if you do not just put down these symbols and formulas and calculations without any text. Okay, exercise number 6. This is a nice abbreviation so that we don't have to write down let phi be a homomorphism of groups G and H. We simply write phi is an element of hom GH, meaning exactly that. And we have to show that for every integer, it is true that phi applied to G to the n is the same as first applying phi to G and then raising to the power of n, now in the group H. And as hinted in the exercise, this is a classical situation for using a proof by mathematical or complete induction. We do this first for the non-negative integers, so the natural numbers including 0, and then we reduce the second case to the first one. All right, our base case here is not n equals 1, but n equals 0. If that seems strange to you, that's always possible. You could also start with n equals 5 or n equals minus 3, as long as you climb the ladder up towards infinity in the natural numbers. Induction always works. So for n equals 0, it is almost trivial, but not quite. We start with the left-hand side. This is phi applied to G to the 0th power. This is by definition the neutral element of G. And now using exercise 1, we know that this here is the neutral element of H. But by definition, if I raise any element of H to the 0th power, I end up with the neutral element of H. So this is true. But we used one fact that we proved before. All right, that settles the base case. Now, the inductive step, we assume that this here is true for some natural number. This is called the inductive hypothesis. We do not say that it is true, we simply assume it is true and show that then in this case, if it is true, then also the statement for n plus 1 is true. And then by mathematical induction, we conclude that this is true for all numbers starting with 0 up to infinity in the naturals. Okay, this here is always true in every group. And now we use the fact that phi is a homomorphism. We also use that here, because in general this isn't true. For any map between groups G and H, this need not be true. Now, by the inductive hypothesis, we know that this here is the same as phi applied to G to the power of n But this expression here by the power law in H is the same as phi applied to G to the n plus first power. And this finishes our inductive proof for this case here. So by mathematical induction, it follows because it's true for 0, then by this step here it's true for 1. But if it's true for 1, by this step it's true for 2, and so on up to infinity. Okay. Now for the case of a negative, or of all the negative integers, we use this here. We also proved this when we proved the power laws in groups, that g to the n is always the same as g to the minus 1, so the inverse of g to the power of minus n. But if n is negative, then minus n is positive. And now we can use what we already proved above, namely that this here is true. We can pull out the power because this is now a positive integer. You know, we already proved this statement for the positive integers. And then we know by exercise 1 that phi of g inverse is the same as phi of g, and then taking the inverse in h. And then by the same trick here, which is simply the power law that we proved way back, this is the same as phi of g to the minus 1 times minus n, and this is simply n. So this settles the case of negative integers, and then we are done. This, of course, is a very useful fact when working with homomorphisms, and the proof is not completely trivial, at least if you're a beginner. So I hope that was understandable. And as always, if this is new to you and you manage to do the proof by yourself, please write a comment and I will be happy for you. All right, exercise number 7. We are given a group G and we fix an element lowercase g in the group G. And now we are supposed to construct a map from the integers to G that is a homomorphism. Oh, we don't have much choice. If n is an integer, we must map it to some element of the group that has something to do with G. So what else could we do than take g to the power of n, where n is an integer. This clearly again is an element of G. Now all that we need to check is this indeed a homomorphism? So we start with this expression, and remember in Z we have addition as our group operation. So here we write m plus n instead of m times n. So this is g to the power of m plus n. But now by another power rule that holds in any group, this is the same as this. We proved that way back. Was a bit tedious to write down, but now we are happy that we have it, because now we see this is phi sub g of m times phi sub g of n. And this here is now the multiplication or operation in our group G. And that's all. This is the homomorphism property. So we clearly have a well-defined map that sends an integer to a group element, and it satisfies this condition here. So we are done. So we see that there are always a lot of homomorphisms from the integers to any group G. By a lot I mean I can take any arbitrary group element, and this is associated with this homomorphism here. Okay, now we show that actually any homomorphism from the integers to this group G is of this form. So we're going to show that psi is phi sub g for a suitable group element G. The hint says we should take a look at psi of 1. So psi of 1 is some element of G, because psi is a map from the integers to G. So this clearly here is a group element that I call G. Then the following is true for every integer n. Psi of n is psi of n times 1. So let's first take a look at the positive integers, so the natural numbers. Psi of n is psi of n times 1. This is 1 plus 1 plus 1 plus 1. And this is nothing but psi of 1 to the nth power. Why? Because this is exactly what we proved in exercise 6, except that here we are not in a multiplicative group, but in an additive group. So 1 to the power of n is written as n times 1. Or you could simply convince yourself of this again using induction or doing it step by step. Psi of 2 is psi of 1 plus 1 is psi of 1 times psi of 1. This is psi of 1 squared, because psi is a homomorphism. So this is nothing but g to the n. This looks good. Also for n equals 0, psi of 0 must be the identity of g. Why? Because psi is a homomorphism, and we proved exactly that a homomorphism maps the neutral element always to the neutral element. And the neutral element by definition is g to the 0th power. So also for n equals 0, this looks good. Now for the negative integers, I write them as minus n, where n runs through the natural numbers. I have psi of minus n is psi of n inverse. Why? Because homomorphisms map inverses to inverses. I hope that's still on camera, otherwise you will see it here. So, but what is psi of n? N is a natural number, so this is g to the n inverse. And by the power law, or a power law in any group, this is the same as g to the minus n. So this shows that psi is exactly the same as the homomorphism phi sub g if we define g in this way. Why? Because psi and phi g agree on all on all the integers. Psi of n, psi of 0, psi of minus n is always the same as phi sub g applied to n, because by definition this is what phi sub g does. All right.